So we did a lot when we covered transformers the other day. And one of the things you guys aren't going to like is when we start getting to real transformers, we start making approximations. And you guys have been trained from day zero to not approximate anything. I know how that goes. Like you were counting up the sides of the transformer, right? So this gets into some approximations that we'll go through a little bit. But I want to go back to where we were with the circuit model. Right? We said there were two types of circuit models. This was our basic transformer. Now we had a process the other day that we kind of went through to try to get to an electric circuit model. It's like at the end of the day, you're electrical engineers, you got to hook things up to an electrical circuit, right? The magnetic circuits really just help us to think about how the device works. Okay. So we had kind of a process that we did to develop an equivalent electric circuit model for this thing. Okay. And the process that we kind of walked through, I've got it, but what was the first thing we did? We looked at this thing and we said, what did I have to do once I had this picture? This is what it would look like.
Magnetic.
Draw the magnetic circuit. All right. Once I get the magnetic circuit, what are my sources in this magnetic circuit if I were to draw it for this? Well, the coils are the sources, right? So in the magnetic circuit model, how do I represent those coils? As MMFs, right? So in this case, help me draw the circuit. How would I draw the magnetic circuit for this thing that I've shown here?
Source.
Well, and how many sources do I have? 2, right? So I have one that's N1, I1. And I have one that's N2, I2. And I just put them in the same direction. Why? Why would they be in the same direction? Their flux goes the same way. And I can always verify that with the right-hand rule. All right. Now, the thing I'm saying here is that this core is pretty much at least ideal. What would make this core ideal? If mu goes to infinity, the reluctance of the core, which is its length over mu times its area, becomes 0. Okay, like that. So I have this set up. All right, so we draw the magnetic circuit, and what do we solve for in that? Flux. All right, we solve for the flux. And when I look at this here, this flux is always going to have 2 components, right? So if I say from the perspective of a given coil, let's say I'm looking at coil 1, right? Coil 1, from his perspective, that flux phi basically has 2 pieces, doesn't it? What would the 2 pieces be? Well, so something I defined a little bit the other day. Basically, I said that this guy had a phi self and a phi, what's the other term? Mutual, yeah. A mutual and a self term, all right? The self term obviously comes from what? Self? Well, the self term comes from itself, right? So from coil 1 makes the self flux in coil 1. And the mutual flux comes from the other coil, right? So basically, that's our way of thinking about it. The mutual flux comes from the other coil, right? Now, if I want to get to the electric circuit model, what were the steps from here? Well, how do I get to the electric circuit model? Get the flux linking each coil, right? That's lambda, right? How do I go from phi to lambda? Yeah, multiply by the number of turns, right? And then I can convert that to a voltage. How do I convert that to a voltage? Take the derivative, right? That's Faraday's law, basically. V equals d lambda by dt. And then I have a circuit model, okay? Now, in that circuit model, what are the only kinds of components that are going to be there? Right? So in the world of circuits, right, we have R's, L's, and C's, right? So what's going to be in the circuit model? Well, Well, yeah, so it could be, so we had two ways of looking at this, right? We said one way is that I could have dependent voltage sources, right? The other way I could do this is I could basically just have inductances. Okay. So again, what we ended up with last time, and I will, let me pull up real quick. In the notes that I uploaded with my transformer stuff, I put at the end of that some summary stuff, right? So one of the things that I had in my summary, this was the mutual inductance view, so I could take that kind of a circuit perspective. Or where we ended up with last time, we didn't get quite all the way there to it, but we can then get a circuit model that looks like this. And this is where I've got a quote unquote ideal transformer. Okay. All right. So that's this. If you go to the notes that I uploaded, you'll see this. These are the, there's a lot of stuff there where I do derivations, but for most likely the last 3 or 4 slides are what you probably care about. They've got the formulas that you're going to want to go to. Okay. All right. So with all that said, the typical approach that we use, we're going to use this when we look at all kinds of fancy stuff later, is pretty simple, right? I build the magnetic circuit. I solve for the flux phi. I go to the flux linkage. Lambda equals n times phi. The other thing to remember is that lambda is Li. So it's the flux capacitor. It is the thing that stores flux, right? Just like I have Q equals C times V, I put a voltage on a capacitor, I store a charge. Put a current in an inductor, I store a flux, right? That's our basic approach, right? Then I take the derivative of that to create the electric circuit model. Now, does Faraday's law work with DC stuff? No, it does not, right? If I have a DC current, that doesn't create a changing magnetic field, so it doesn't create a voltage. So that means that we're always dealing with AC stuff. So V of t equal to d lambda by dt. If I'm working with phasors, if I'm working with AC stuff, I can go to phasors, I guess. So how can I write that in phasor domain? The voltage phasor equals what? Instead of d lambda by dt, j omega times lambda. This would be a lambda phasor, okay? Which, if lambda equals Li, it's j omega times L I, right? So I always get that kind of relationship, all right? The model I end up with better only have inductances. If it has other stuff, I totally screwed it up. There's no way there can be a capacitance that comes out of this thing. And there's no way a resistance can come out of this thing, all right? It better all be inductances, okay? So, all right, so we ended up the other day talking about what I would call sort of a real transformer, not an ideal transformer. So I want to build a magnetic circuit model for this guy. If I had a real transformer model, what's going to be different? Well, one thing is it's ultimately not going to be lossless. So if I say it's not lossless, what's that mean? Power is not the same on both sides. So in other words, there's some losses, there's some heat. Real transformer like the one I showed the picture the other day, if you touch that transformer, it's hot, okay? I guess I took the picture out, but if you looked at the picture of the transformer I had the other day, I had vents on the top of it so that air could flow out of it, okay? That's a common, you have to do that. If it's a big transformer, it'll be submerged in oil, right, for cooling it. And there's pumps that'll actually circulate the oil around it. All right, so if transformer gets hot, it's got losses, real transformer. Let's forget the losses for a second. All right, the losses deal with what's going on with the conduction and everything. But if I talked about the magnetic parts of this circuit, what would make, so what we said the core, if the core is ideal, what's that? What did that mean about its reluctance? 0. So a real core is basically going to have a mu, which is much, much bigger than mu naught. But it's not going to be infinite, right? It might be, we said for a real magnetic material, maybe it's like 10 to the 3rd to 10 to the 4th times bigger than mu naught, okay? So if that's the case, how would that change the magnetic circuit? What does that change about the magnetic circuit? So I showed some of the flux here, but there's actually some other flux, right? What's true? So what the fact that mu is much, much bigger than mu naught, what's that mean in terms of the magnetics here? What would that mean about the fluxes?
They're very big when
Well, not the fluxes. So let's say I told you, okay, you had a voltage source, all right, and you hooked a resistor up to that voltage source, all right, and I told you the wire was more conductive than air, but not perfect. What would that mean about the charges coming out of that voltage source?
lost in the air.
There would be some current going through the air that would be basically bypassing that resistor. Now, it wouldn't be a short circuit. There would be some resistance to it, right? But it would basically mean that the charges would not stay in that wire. In the case of an inductor, what that means is that some of the flux is going to quote unquote leak out of the core. All right. So how should I draw that? How should I draw a flux that leaks out of the core? So it's basically saying it's a flux that doesn't make it to the other coil. It doesn't go all the way around. What does it have to include? Well, it has to include the coil that created it, right? So basically what we say is the flux that goes around like this. So I'm showing it like that. The total flux going through that coil is the flux that goes through both of the coils plus the flux that leaks out. So I'm going to call this guy here, well, which direction does it go? Which direction does this flux go? Right-hand rule. So yeah, so my finger goes in the direction of the current, my thumb goes in the direction of the current, my fingers curl up, right? So basically this guy is going to go up and he's going to come out. Where does he come out? I don't know. It comes out all over the place, right? This is just a way of thinking about it, right? If I wanted to get real careful on it, I'd have to do calculus and it would be nasty. We don't really care that much about it. We just know that it exists. Okay. Now, what would it look like on the other side? Which way would it go? Not sure that I can follow it turned around, but it would go.
It's kind of the same direction.
Tell me clockwise or counterclockwise? Clockwise, yeah. There we go. It would go clockwise. And I'm going to call this here, I'm going to call this phi L1, and I'm going to call this phi L2. Okay, like that. L for leakage. All right, so this is leakage. It's flux that's leaking out of the system. All right, so help me draw the magnetic circuit for this. All right, help me draw the magnetic circuit for this. So basically, the way I think about this, phi L1 and phi L2 and phi, we got three fluxes that are going on here. The flux phi goes through both of the coils. It's the flux that makes it all the way through. So I'm going to say I got a reluctance of the core like that, and there's a flux phi that goes that way. Where would I put those MMF sources? Well, in parallel with the R, I get, well, I don't know, they're in series with the R. So they'd be like that. That's the same thing we had before, isn't it? N2, I2, N1, I1. Why did I draw them in the directions that I did? I'm not done with my circuit yet. There's more reluctances to it. All right. But N1 and I1 and N2, I2, they're in series with each other. Why does that make sense? Why would they be in series? They're pushing the flux both in the same direction here. Now, what I add is I'm going to add the reluctances of those leakage paths, right? Where would they be? In parallel with what? In parallel with the sources, yeah. So this would be phi L1. This here would be phi L2. Give myself some more space. This would be phi L2. This would be N2, I2. And this would be the reluctance of whatever that path is, right? And I need more space. This would be the reluctance of that path. And this would be phi L1, right? So if I did a KCL, what's a KCL in this case? So sum of the fluxes, right? So if I went up to basically if I want to figure out, let's say the flux linking coil number 1. All right. If I want to get to the flux linking coil number 1, there's 2 ways for me to look at this, right? The way I look at this is if I look at that picture over there, the flux linking coil 1, what's it have to be based on this picture? There's 2 fluxes there, right? What would it be? Well, it's what phi is, right? And it's what phi L1 is. It's the 2 of those. So I better be able to KCL that here, right? So if I look, this is the flux through coil 1 right there, isn't it? If it's going through the MMF source, that's coil 1 is that MMF source, right? So I've got phi 1 equals what? I can KCL this and say phi 1 equals phi L1 plus what?
Is that the mutual?
Phi 1 is the flux. If I was saying the mutual flux, I'd put an M on it, right? It's just the total flux. The flux linking coil 1 is whatever phi L1 is plus whatever phi is. Okay. All right. If I were to go through this thing and I were to do some analysis on it, phi L1, you guys should be able to tell me phi L1, what is that going to be based on that magnetic circuit picture I did there? N1I1 divided by RL1, because I just have a single loop right there, right? So I've got basically just an Ohm's law thing where I can say N1I1 divided by RL1 is that leakage. Okay. And then how do I get the rest of it? I can do a KCL around the outer loop, can I? Or KVL around the outer loop, right? If I do a KVL around the outer loop, it'll tell me what phi is. So how do I do KVL around the outer loop? What would that be? So around the outer loop, basically meaning going through the 2 sources, right? And the reluctance of the core. So what would that be? What over what?
1I1 plus N2I2 over RC.
N1I1 plus N2I2. I'm going to write it this way on purpose. Right. So what I ended up with is, where's the mutual flux here? Which one of there's 3 terms now. Basically, in a real transformer, this is what you get. You get 3 terms in those fluxes, right? If I tried to give these terms names, because I don't like to just look at the math, I like to think about what they are physically, right? Which one of these is the mutual flux? This one, yep. The one coming from the other core. This is the other coil, sorry. This is the mutual. This is what I would call the leakage. And I don't know, I need to get too worried about this, but I guess I'll call this the self-magnetizing flux. We use the term magnetizing to mean it's going through the core. All right. If it's going through the core, it's a magnetizing flux. All right, because it's magnetizing the core. All right. If it's going through the leakage path, then it's the leakage. Okay. No, normally it's the case that the flux going through the leakage path is a lot smaller than the flux going through the core. All right. The leakage path flux should be smaller. All right. Why should it be smaller? Why should the leakage flux be a lot smaller? Because the permeability of that path is
Smaller, right?
It's hard to think that through, right? Basically, the way I would say this is it would be a really bad core, right? This would be a really shitty core Let's put it that way. Be straight honest about it. If I had a lot of leakage, the core's not what's the job of the core? The whole reason for the core is what? Is to direct the flux from coil 1 to coil 2. Right? So if the leakage flux is a lot, it's a bad core. All right? Go get a new material or something. All right. So that's the kind of the core takeaway. It better be the case that those leakage fluxes are small, meaning that the reluctances should be large and the permeabilities should be small. All right, but let's think of it this way: if the core is good, leakages are small. All right, and it's the case that the core should be good. You don't make an air-based transformer, right? All right, you make an iron-based transformer to try to guide the flux. All right, so what we ended up with last time was basically, I said, okay, for something like phi 1, I would get this N1 over the reluctance of the leakage path times I1 plus N1 over the reluctance of the core times I1 plus N2 over the reluctance of the core times I2. You guys told me, when I get to a circuit model, what do I got to do next? I got to get to a lambda, right? That's a flux linkage. That's how much flux is linking the entire coil, right? So when I'm doing that, I'm thinking of this thing as a series of inductors together, and I'm putting them all in series. So how do I get to that? This lambda is a what? How do I write this? N times phi. So, and it's specifically N1 times phi 1, right? So it becomes N1 squared over a reluctance plus N1 squared over a reluctance times I1 plus N2 over the reluctance of the core times N1 over I2. Now, when I have turn squared divided by reluctance, what do I have with that? I have an inductor, right? So I can put the inductances in now, or usually what I do is I jump ahead to the voltage equation, right? How do I get to the voltage equation? Take the derivative, and if it's AC, I can turn it right into phasor stuff, right? So instead of d by dt, what's a d by dt in the world of phasors? J omega. All right, so this guy becomes J omega N1 squared over the reluctance of the leakage path plus J omega times N1 squared over the reluctance of the core. I need my currents. Plus J omega times N1, N2 over the reluctance of the core times I2. Like that. All right. What we said is, I give this guy a name. This N1 squared over the reluctance of the leakage path. No one knows what the reluctance of the leakage path is. Right. What they often know is what I call this. So which is, for now, I'm going to call it L leak 1. It's the leakage on the primary side. Leakage inductance is the name I'm giving this. All right. Plus J omega times what I call L mag. I call that the magnetizing inductance. Plus J omega times M times I2. Okay. In the notes so the notes that I uploaded define all of those terms. What's M, what's L mag, right? When I look at this, what the other jump that I make, right, is I make the statement that if I take, so this is what I just wrote on that last page right here, okay, where M is equal to N1, N2 over the reluctance of the core, and I had that L mag equals N1 squared over the reluctance of the core. So what you see here is, how could I write M in terms of L mag right there? How could I write that? Yeah, so yeah, I could say this is N1 over N2. oops, other way around. N2 over N1 times L mag. All right. I did that here. All right. I did that there. And then I also, yeah, I did that. Did that there. That should be I2 though. Right there. What I do is I then group those two terms and I gave this a name, I mag. All right. Now, magically next to this thing, I drew a circuit, right? So if I were to look at, so basically what I wrote here, the voltage equation would be J omega L leak 1 times I1 plus J omega L mag times I mag. That yields a circuit that consists of those three things in series. Okay. Right? So how would I verify that right there? So this right here is something I got from just looking at what was above it, right? How could I prove that that matches that circuit? KVL, right? So if I did KVL around that circuit, I'd have V1 equals J omega times L leak 1 times I1 plus J omega L mag times whatever I mag is. So that makes sense. And what I hung off of this thing is, what do I call this thing here? This thing in the box with the dots. Ideal transformer. Are those two things in here, are they inductors? No, they're not inductors. That thing together with the two coils in it is an ideal transformer, which is its own circuit element. All right. What I did here is I said, this current over here is N1 over N2 times I2. Where the heck did I get that from? And why do I have it go in the direction that it's going? Where did N1, where did I get off saying that that current is N1 over N2 times I2? Did I just make that up? Well, from the current relationship that I have for that ideal transformer, right? So if basically the primary side current, so if I'm thinking of this here, this is the primary side current, right? That's how I get to the primary side current, right? Now, one question I want to ask myself is, why is it going the direction that it's going?
Dots, like if it goes there.
Because of the dots, right? So in this case, how have I drawn I2? I2 is going into the dot. So where's, I1's on the other side of this thing here, on this ideal transform, but the current coming out of that dot is going to come out of the dot because there's a current on the other side going into it, right? That's our basic relationship. That's why I drew it the way that I did. And so if I do a KCL right here for this I mag, what is it? It's I1 plus N1 over N2 times I2. So everything about that circuit is consistent with what I just did from the magnetic circuit. Now, this thing right here is what every magnetic device looks like. It's got leakages and all that stuff, all right? So that is our basic model for a real transformer, with one exception. What does this still not include? Power loss. Still doesn't include power loss. Okay. Now, problem 3 in your homework, we talked about this last Monday, right? In a real transformer, what kind of losses do I have? I talked about it from an inductor perspective, but in a real inductor, I got losses that come from where? Well, losses are heat, right? The conductivity of the core, right? The fact that there's eddy currents that are being induced in that core, the fact that there's magnetic materials moving around and all that sort of stuff. Where did I place that loss? Right. So I said the core loss, we talked about that. You had problem 3 on the homework. Where did I put the core loss? There was a resistance in parallel with that magnetizing inductance. There was a resistance in parallel with the inductance coming from the core. We haven't touched leakages until this moment. right? But it was in basically the inductance of the core and the loss of the core were in parallel with each other. And then the other thing which I didn't include is I also probably have a winding resistance, I call it. What's the winding resistance? Yeah, the wire has some resistance to it, right? So at the end of the day, the whole circuit model ends up looking like this thing. Okay. And I didn't include this. I could have written out, a whole equation for lambda 2, but we'd be here for another 2 days and you guys would fall asleep. So basically what I end up with is this. All right. And R1, or what I call RP and RS here, that's the resistance to the primary side, resistance to the secondary side. And then there's a resistance to the core. All right. Now, the thing that we're going to find out here as I go through this is LMAG and R core are going to be big. All right. So much so that they're not really going to be significant. All right, is what we'll find out in terms of the analysis that we do. You look at a typical power transformer, like the one I showed the other day on the nameplate, it doesn't even tell you the LMAG and the R core, but it does tell you about the leakages and such. All right, so we'll see more about why that is a little bit. All right, so here's kind of a summary of all that. All right, for my real transformer. So basically I have what I see for V1. All right. And then I've defined what my IMAG is. So IMAG is the current in the magnetizing inductance. And basically the way I think about this is it's sort of the equivalent current that is magnetizing the core from the perspective of the primary. And that's a lot of big words and probably won't mean much to you. But it's basically saying if I took the secondary side current and moved it to the primary, and thought of basically the secondary and the primary as just having one inductor to them, that's the current that would be going through it. All right. And then I defined out all this other stuff on the inductances themselves. Okay. All right. So a lot going on there. All right, but it's really not that confusing. All right. It seems like a lot when you're kind of deriving it, but when we start using it, it won't seem too bad. All right. Now, any questions about that? Many questions, and you don't know what they are yet, probably. Musa does, though.
So
Yeah.
the current going through the magnetizing inductance, that goes through just the magnetizing inductance.
Just goes through the magnetizing inductance. Yeah. Okay. And yeah, this is kind of arbitrary. We throw in the core resistance and we throw in the winding resistance. Everybody gets all kind of tied up in knots about those things, but we're talking about very small resistances. And if I measure that resistance at low load versus high load, heating's going to happen and those resistances are kind of going to change. And we don't tend to worry too much about those numbers so much. All right. Basic idea is that we understand what this model is. All right. So, all right. I want to get to sort of a basic problem though. And one thing that people might remember from like a circuits 2 is there's a way to basically do something called impedance reflection. Because what I'm going to do is this model is ugly and it's not the one that we typically use. To be honest with you, the model that we typically use, a power engineer, for instance, simplifies this down to this. Usually able to get rid of the magnetizing stuff. All right. And turns this all into sort of one series RL. All right. There's a way of doing that. To do it though, I got to use this impedance reflection idea. Okay. So let's say I said to you, I put a voltage source over here. Okay. So I put a voltage source, and is it AC or DC that I put here? AC. If I put a DC source over here, V2 ain't gonna do anything. All right. Why is V2 not gonna do anything? So in other words, if this was a DC, if I put a DC battery on the primary, there'd be no current on the secondary, right? Why is that?
Short. Switch to one.
You stated the result of it. Yeah. Basically, the statement is that Faraday's law tells us that if I don't have a changing magnetic field, then effectively what I have is there's no voltage created. Basically, that leads to it being a short circuit. All right, but which is basically, yeah, it's not gonna create anything over on the secondary side. All right. So what would I do here? This is an AC source. All right. How could let's say I want to solve for I1. Okay. Well, what would I do? How would I approach this? First of all, what's I2 going to be? What's the current on the secondary? And which direction is it going to flow? Based on the picture that I drew here, let's deal with the directions first. There's I2 current on the secondary. Where's that going to be? Which way? Let's go out of the dot, right? And if you think about it, I mean, this makes good sense. And this is kind of the way the world generally tends to work. A current goes from the source to the load, right? So it's going into the dot, out of the dot. Into the dot on the primary, out of the dot on the secondary. So I2 is going that direction. All right, now, how do I figure out what I2 is? What would that be in terms of what I've shown right here? I2 would be what? Yep, V2 divided by Z. V2 divided by Z. All right. Now, how can I express that in terms of, let's say I want to figure out what, how can I do that in terms of V1, the primary side voltage? Well, let's write off to the side. What are the relationships for this transformer, right? What are the two relationships? There's a voltage relationship and a current relationship. How do I relate the voltages? V1 over N1. And the way I always think about V1 magnitude over N1 equals V2 magnitude over N2. And then I just think about the signs. All right. What's the other relationship I have for the currents? I could get it from a power relationship if I wanted to. But N1, there's an N1 and an N2. How about that? I'll spot you that much. N1, I1. And I always think of it in terms of the magnitudes. And then I use the dot idea to think of the signs. All right. Based on the signs that I have right here, it's just simply, I've got my signs correct already, right? So N1, I1 equals N2, I2. And if the voltages, if both the positive signs are at the dot, which they're pretty much always going to be, the magnitudes match. All right, I'm not going to give you a weird one where the plus signs, one's at the dot and one's not at the dot. What do you mean diagonal?
Like one dot would be on the top, and then the second dot would be on the bottom.
It could be, but I'm not going to do something weird like that. Yeah. Yeah, it could. Well, yeah, nowhere two is it's basic training, right? You're jumping through the tires and you're climbing up walls. In reality, it's not basic training anymore. This is what we're likely to see, right? I'll try to keep it to the sort of the reality of things. All right. So, all right, so I got that. Then if I keep going with this, I say, okay, well, I got my relationship here. So that tells me if I want to put this in terms of V1, help me put V1 in here. Okay, yeah, so it's N2, N2 over N1 times V1 divided by Z. like that. All right. Now help me figure out what the current's going to be on the I1 side. What's that going to be? How would I figure that out? I can use this relationship, right? This was I2. So I could say I1 is equal to, how would I, yeah, so this would become I1 is equal to, let's see, let's do it this way. We have I2. Let's just write it, and N1 I1 equals N2 times whatever I just did there, right? So N2 times, so it'll be N2 squared V1 over Z, like that. Okay. And there's an N1 right there. Okay. All right. So what is I1? I1 is N2 squared over N1 squared times V1 over Z. Now, what I typically do is I rewrite this a little bit, and I rewrite this as V1 over I1. Right. So I basically just rearrange it. V1 over I1 equals Z1 times N1 over N2 squared. Right. That's just a rearranging of the math. Right. What is V over Z, V over I? What units does that have? Ohms, right? That's an impedance. So what I sometimes call this is a Z effective or a Z equivalent. It's basically saying, if I put a voltage onto the primary and I measure the current that goes into it, the current that I measure is basically being drawn by this equivalent impedance, right? So it's basically taking into effect the effect of the transformer and the load together. And so this is called impedance reflection. So you take the impedance and you multiply it by the turns ratio squared, all right, is what I end up with. Now that turns out to be a pretty useful thing in a lot of ways when you're solving circuits, right? We do that a lot. It also helps us to kind of simplify this circuit a little bit. All right. Without going through the details, because again, I don't want to lose you guys in derivations, right? If I were to take this idea right here, and I look at my transformer model, right? So let me go back to just my transformer model, right? So I have an impedance over here, a leakage and a winding resistance on this side. Okay. I can take that impedance and I can reflect it over to the primary side. Okay. And when I do that, this is what I end up with. You can show, and again, I don't want to go through the details of this, but if you do a KVL, you can find out that basically what I just did here is going to give me a completely equivalent set of relationships if I do that. Right. Now the resistances here, right? What I have is it has the turns ratios in them like that. All right. So I get the same basic thing. Now, the thing that I've added here is I've got a voltage across this magnetizing component or whatever, right? So I've added a term there, but this is the basic idea of what you get, and you would hook your load up on that side. So you're basically kind of getting the secondary kind of all by itself. And again, it's not hard. If you want to prove that to yourself, do the KVL relationships, and you can see that sometimes we call that the T model. You can show that that's entirely equivalent. Okay. Now, again, then we make an approximation. All right. I can make an approximation that I'm going to move that core loss and that magnetizing inductance over. All right. Now, if you did what I just did here, and I took this guy right here, and I moved it there. Okay, in other words, I just did that. I moved it over. If you did that to Yahoo, Yahoo would be very upset. He would do his sad Yahoo face, right? And why is that? Why would he be sad? No, I'm not changing the frequency. First of all, can you just move stuff around in a circuit? Can I just take impedances and move them? No, I can't do that. That doesn't make any sense, right? In other words, this and this, if I just taking that and moving it over, right? There's, KVL should still be true, right? So if I put a voltage right here, right? So say I put a voltage source right there, V1. Yeah, there'd be a current going through this, there'd be a loop right there, right? The current through this inductance and this resistance is not the same if I move this over to here. Right? So that'd be sad Yahoo time if you did that, right? You can't just do that. So how is it that I can get away with that? What would make that possible? Well, all right, let's look at it like this. Like, let's say I had this circuit. All right. And let's say this is the same thing as me saying, all right, I don't like this resistor. I'm just going to get rid of it and say I got 1. Right? How can I do that? How can I just erase a resistor? What would allow me to say if I have 2 resistors in series,
Very small.
if one of the resistors is very small, then it's pretty, so let's say this guy is 1 ohm and this guy is 1,000 ohms. Then I could basically say these 2 circuits are the same. Like that. That's basically what we end up saying. All right, now, in fact, what I really kind of do is I say, you know what, the current in this branch right here, the current here is so small, all right, that the current flowing through here is so large that I can ignore, I got to be careful with the way I say this, right? Moving this over to here only works if these are small values. Now, I didn't just erase, so on the bottom here, I just erased this resistance, the small one. Here, I didn't erase it. I said, well, I'll move it over to the other side, right? Now, that's even weirder, right? I didn't get rid of it. I kept it. I just moved it somewhere else. So why did I do that? Well, because the real reason is that the current here is very small, right? So that current is small. I want to keep it, right? Basically, what I'm saying is at this point right here, if I'm really operating this thing as a transformer, all right, and this is maybe the key point. If I'm really operating this thing as a transformer, from a KCL perspective, most of the current that goes through this branch right here is going to be really small. Okay. The current going into this branch, basically, I should say it like this. If I look at the way this guy says IE and I1, basically IE is much, much less than I1. And I should say it in terms of magnitudes. IE is much, much less than I1. If that's the case, then I can kind of put that guy wherever I want him to. From the perspective of trying to figure out IE1, I can say that these impedances don't matter. And from the perspective of the currents, basically the circuit gives me the same result. This is just an approximation that only works if the impedance, if the magnitude of XM1 in parallel with RC here, if that magnitude is much, much greater than the combination of R1 plus JX1. All right. Basically this set of approximations holds up. All right, they're approximate, and we're gonna do some numbers to kind of see that those approximations make sense. Okay. All right. So here's what we're gonna do. We're gonna try to understand and develop that circuit model a little bit better, right? And this should not say VOC. I don't know where this came from. This should say POC. All right. So let me Here's our equivalent circuit. If I take this circuit right here, and I want to take this load off of the circuit for a second. All right. All right. Okay. All right. So let's say what I did is I put a voltage source right here. Like that. All right. And I leave the secondary open circuited. Okay. How much current do I have in this branch right here? If I have this arrangement, what's that equal to? If I have an open circuit on the secondary, what is this I2 prime? 0. Okay. So what I do is this, if I have this arrangement where I leave this thing open circuited, where is all the current flowing? Yeah, it's basically all into this branch right here. Okay. So what I did, this is sometimes this arrangement that I just wrote out here. This is sometimes called the open circuit test. All right. So when people figure out the parameters, and this is what you do from an engineering perspective, nobody knows the reluctances of the different paths or whatever. From an engineering perspective, what I typically just know is things like this. I do a test where I hook up a voltage source, VOC. I call it VOC, right? And I hook it up to the transformer. And I have just this. This is LM and this is R core. Now, technically, there's this other stuff in parallel with it, right? But there's no, it's not there. This is the basic circuit I have, right? So I'll call this IOC like that. So it's weird saying I had a current and an open circuit, but basically you're saying it's just the secondary side is open circuited, okay? And I measured a power of 400 watts when I did this. All right. So let's say that's the case. All right. So here's the circuit we're going to analyze. I've told that this is 8,000 volts. And I've got a current that was flowing into this thing that was 0.214 amps. All right. So I know this, the magnitude of this current. Magnitude of that current is, give myself some more space, 0.214 amps. All right. And there's a R core and there's an LM. Like that. And I was also told that the power that was being delivered here is 400 watts. Okay. And what I want to know is the parameters of this guy. I want to know what's RC and what's LM. What are those parameters? So what are they? How would I figure that out?
Power is V squared over R, right?
The power is going to be V squared over R. Yeah. All right. You know, the power is going to be V squared over R. So how do we know that? This is kind of similar to what you have in problem 3, I think, in the homework. It's pretty similar. Problem 3, you do have to calculate some things about the loss to figure out the power, right? But I know that the power is going to be VOC squared, right? This was my VOC. VOC squared divided by R core. Okay. Well, which is also the real part of the impedance. Now notice this is an R, not one of those script R's. Script R's would be, I would talk about a reluctance, right? So what is this? VOC squared divided by the reluctance of the core. Well, so that would be 8,000 volts squared divided by whatever the reluctance of the core is. And that's equal to 400 watts. So if I do the math on this, I get that the resistance of that core works out to be 160 kilo ohms. Pretty big. Okay. What was it that we said was going to happen? Well, we said that for a real device, it better be the case that the resistance is here, right? We were moving this stuff out. Oh, it's kept there now, right? We basically said that this guy here was going to have a really big impedance so that the current going through it was going to be pretty small. And that's kind of what's happening, right? The current that I have here in this setup, 0.214 amps, is pretty small. All right. And the parameters that I took here, this was for a 20 kVA transformer. All right. I said I rate my transformers in apparent power. Okay. So 20 kVA, if you said 8,000 volts, right, that's a pretty small current that I have flowing in this thing. Okay. All right. So I've got the power that gave me the R sub C. Now, how do I get to the L? How can I get that? A couple of ways that I could do it.
You know, the amount of power and the real power, can you find the reactive power?
Well, there's a couple of ways to approach it, right?
Well, if you find the reactive power, you can find the current about doing monthly, right? And do it the same way that we did resistance, just barely.
If I find the reactive power, yeah, I could get the reactive power. How would I get? Yeah, sure. How would I get the reactive power?
We'll use P and S to find the power factor.
Yeah, so I got a couple approaches here, right? So one approach would be to say I could figure out Q. Right? How could I figure out Q? So let's go to our triangle, right? So first of all, in our triangle here, here's P, right? Where's Q? It's the imaginary parts. Go up or down? Up, right? Why is it going up? It's inductive, right? So, and he's got actually a lot of Q, right? It's a bad drawing of it. It's got a lot of Q. All right. Here's the magnitude of S. Not S, but the magnitude of S. What's the magnitude of S? Yeah, so 8,000 times 0.214 is what it is. Not necessarily that 20 kVA. I did it a different. Let me see. I didn't write down what that was. 8,000 times 0.214. I probably did somewhere. What'd you get? 1712. Okay. All right. And what are the units? The volt amps. Okay. All right. So I got that. Now a couple of ways to do this. Like if I wanted to get the Q, how would I get the Q? I use the Pythagorean theorem and I could say magnitude of S squared equals what? P squared plus Q squared. And solve that for Q. All right. That's not what I did, but that's a way to do it. Okay. And then, you could then say Q is equal to what? You would say voltage squared divided by what? Yeah, the imaginary of Z, which is X sub M here. Okay, that'd be one way to do it. Now, the way I actually did it was I said that I have R core and I have XM like that. And I'll just write it as XM. So what I did was I said, I want to figure out the impedance looking into there. Now I know the magnitude of the impedance, don't I? Yeah, and I also know let's see, the way I did it, I said the total current here, I. All right, the total current I knew what IOC was. IOC was equal to, the magnitude of it was 0.214. Is that what I said?
Yes.
Yeah, 0.214. All right. What I did was I figured out the current vector. Right? How could I figure out the current vector?
You found that.
Yeah, so how can I find the angle?
Power S, like,
Yep, so I know what S is. And I know what P is. So S times the cosine of phi is equal to P. And I don't say phi, right? What do I say? Phi Z. That's the angle of the impedance, right? So what's that become? Well, so I solved for cosine of phi Z. That ends up becoming 0.2336. All right. That is a very bad power factor. All right. The heck does that mean? I said, what's it bad? So what does that mean? If I have a power factor that is low like this, what does that mean about the load that I have?
It's a lot of the power released there.
Well, a lot of the power is going into which of these two things? Where's most of the current going to be going? Most of the current's going to be going into the inductor. Right? Most of the current's going to be going into the inductor. If it was close to unity, then most of the current would be going through the resistor. All right, that's basically what this means, this low power factor thing. All right, so if I wanted to figure out what is I, so this IOC, if I figured that out as a vector here, IOC would be what? How could I get to that? Well, I know the magnitude, right? What's its angle going to be? So I know what phi Z is. So if I mean, I guess in my assumption with all of this is I said that the angle of the voltage was equal to 0 degrees, right? So basically it would be negative cosine of phi Z, inverse like that, okay? If I do that, basically I end up with 0.05 minus J times 0.2081. All right. So I wanted to do it a slightly different way. So I can look at that 0.05 is going through one of those guys and 0.2081 is going through the other one. Right? Basically what this is saying is, where is the 0.05 amps flowing? Where's that flowing in this guy? The resistor. The resistor is taking the 0.05, right? And then what's the inductor taking? 0.2081, right? Basically, this is the real part of the current. That's the current that's going through here. The imaginary part of the current is what's going through there, right? So basically what I can say is, does that make sense, right? The real part of it basically is the current that is entirely real. It's going through the real component of the circuit. That imaginary component is only going through the inductor because there can't possibly be anything imaginary going on in the resistor. All right. The fact that it's imaginary means that it's phase shifted by 90 degrees. All right. That's basically what it means. So what I can end up saying here, and what I ended up doing is I said XM times 0.2081 equals 8,000 volts. Because I know that this voltage is 8,000 volts. Like that. Okay. And I end up getting that my XM is equal to 38.447 kilo ohms. All right. Pretty big, right? All right, that's much bigger than I would, I say pretty big. That's a big number. That's not necessarily a big number if you're thinking about things from the electronics perspective, but that's a big number if I'm talking about the power world. Okay. And that's a very small current. Now, a question I have is, looking back at this model, the other test I can do is I can say, what happens if I put a short circuit right here? Right? If I put a short circuit right there, well, what's that mean that VP is right here? Well, how does that change this circuit? What's the voltage across this ideal transform if I put a short circuit right there? What's VP? What's this voltage if I put a short circuit right there? 0, right? There's a short circuit across the transformer. So that tells me that what I have here is that this circuit becomes this. Like that. And then what do I do with all this other stuff over here? Well, I can say that it looks like I have this, right? Where this is that R1 plus R2 with the reflected stuff.
Essentially, the transformer is short.
The ideal transform, yeah, so I short the secondary is what I did here. I shorted the secondary out, right? And what I get is this. Now, the approximation I'm making is I said that, what did I say about this current right here? Because these impedances I'm saying are big, I make the assumption that this guy doesn't matter. And I can delete that. Now, what would make that not matter? What makes this branch not matter? IE is small or the impedance of this stuff is big, right? That's the same statement, right? So if I do that, basically then for this short circuit test, that's the other test I have. I basically have this arrangement. So I say I have V short circuit. I have I short circuit. And I have this. So here is R1 plus R2 reflected. And X1 plus X2 reflected. Like that. All right. So how would I solve in that case, given the information that I've got? Right. So the situation that I have here is, I said I've got V short circuit. I know the magnitude of I short circuit. And I have this resistor and I have this here. So this is X1 plus X2 reflected. Oops. N1 over N2. And this is R1 plus R2 times N1 over N2 reflected. All right. And the numbers I was told here, this guy is 489 volts. And this character was 2.5 amps. And that the power was 240 watts. Right? The power is 240 watts. All right. How do I approach this? I told you, all right, and let's give these, this clunky to carry this around. I'm going to call this R equivalent. I'm going to call this X equivalent. Like that. Okay. How do I figure out R equivalent? Let's start there. 489 divided by what? No. That would tell me the magnitude of the impedance if I did that, right? So what do I know about the 240 watts in this case? These guys are in series, right? So I don't know the voltage across that resistor, do I? What do I know about that resistor? I don't know the voltage across it, but I know something. I know the current through it. I know the magnitude of the current through it, right? So what do I know? I know that it's I short circuit magnitude squared times what? R equivalent. So I can solve that to get that, right? And then I could do a similar sort of thing again, where I can say Q. This is the way I did it this time. I said Q is equal to what? S squared minus P squared. Like that. Square root. All right, same thing Cody had suggested on the last one. Then how do I get that now? If I wanted to, how would I get that to give me a X value? I know the Q. Can I do it the same way? Wouldn't that be I short circuit squared times X EQ? Same basic approach, right? And then I can get through this. Now, when I go through this, I get totally different resistances. I get REQ is equal to 38.4 ohms. And I get that XEQ works out to be 192 ohms. These are orders of magnitude smaller than what I just said for the other parameters, right? These guys were 38 kilo ohms, and where's the other one? Did I not write it down? Oh, there it is. It was 160 kilo ohms. So these are orders of magnitude smaller, and they help to justify the approximations that I made. All right. So I made the approximations before I showed you the parameters, but that's you know, it makes sense. Okay. All right. So